Hi everyone, this is the video for class 33 of PH 125, and today we're going to be wrapping up our discussion of the kinetic theory of a gas by talking about the root mean square speed. Then we're going to be talking about phase transitions, and finally we're going to wrap up for today by talking about the first law of thermodynamics. So let's start with a quick review of what we've learned about ideal gases so far. So remember, the ideal gas model is a model that assumes that molecules in a gas do not interact, which is a really good approximation for real gases that have low density. Okay, then we learned that the pressure equation of state for an ideal gas is given by the ideal gas law. So we have two forms that we can deal with in this class. PV is equal to little n RT, where little n is the number of moles in a substance, and R is the ideal gas law constant, 8.31 joules per Kelvin per mole. The second form of the ideal gas law is PV is equal to capital N KT, where capital N is the number of molecules in your system, and K is the Boltzmann constant, 1.38 times 10 to the minus 23rd joules per Kelvin. Okay, so it turns out that capital N, which is the number of molecules in your system, is related to little n, the number of moles in your system, through Avogadro's number. So specifically here, capital N, the number of molecules, is equal to little n, the number of moles, multiplied by Avogadro's number, 6.022 times 10 to the 23rd molecules per mole. Okay, then we learned that the kinetic energy of an ideal gas is related to its temperature. So the kinetic theory of a gas told us that the average kinetic energy, which in general is going to be equal to 1/2 times the mass per molecule in your system, multiplied by the average value of those molecules' speed squared, is specifically equal to 3/2 kT when you have a monatomic ideal gas. Okay, so now we want to talk a little bit more about the speed of molecules in an ideal gas. So the kinetic theory of a gas, remember, told us about the kinetic energy, the average kinetic energy per molecule, and the temperature of the gas. So specifically, we learned that those two things are related. And then remember that kinetic energy in general is related to speed. And so that tells us that the speed of the molecules in the gas is going to be related to the temperature of the gas. And now we want to learn specifically what is that relationship. So it turns out that that relationship is given by the Maxwell speed distribution, which tells us the relative probability that a molecule in an ideal gas has a particular speed when that gas is at a particular temperature. Okay, so over here on the right-hand side of my slide, I have a plot of the Maxwell speed distribution for an ideal gas at two different temperatures, so 300 Kelvin and 1100 Kelvin. And you can see then that the height of these curves corresponds to how probable the different speeds are for the different temperature gases. Okay, so specifically looking at this example here with the 300 Kelvin gas and the 1100 Kelvin gas, you can see that the most probable speed, which is going to correspond to the location of the peaks of the two curves, so the most probable speed for the 300 Kelvin gas you can see is close to like 400 meters per second, whereas for the higher temperature gas, the 1100 Kelvin temperature gas, we can see that it's closer to 750 meters per second. So here you can see that the most probable speed is going to increase with increasing temperature. These distributions can also tell us about the average speed of the gas. So the average speed of a molecule in the gas is going to be a little bit higher in general than the most probable speed, which comes from the fact that these curves, you can tell they're a little bit more sharply peaked on the left-hand side, so at lower speeds, than on the right-hand side. And so that means that the average value of the speed is just shifted a little bit towards higher speeds away from that most probable speed. Okay, so now let's talk a little bit more about the speed that's given or that's associated with the average kinetic energy, which we know is equal to 3/2 kT from the kinetic theory of a gas. Okay, so this speed is given a special name. It's called the root mean square speed, or RMS speed. And in general, the RMS speed is defined to be equal to the square root of the average value of the speed squared. Okay, and then by comparing to the kinetic energy, the average kinetic energy per molecule, which we know is equal to 3/2 kT, we can see that this root mean square speed for a monatomic ideal gas is equal to the square root of 3 kT divided by m, where m is the mass per molecule. Okay, so looking at our plot over here, we can see that this root mean square speed is plotted as well. It's a little bit higher than the average speed. That's going to be true in general, not just in this particular plot. And both of those are higher in general than the most probable speed. Okay, let's just do a quick example on this root mean square speed. So suppose you want the root mean square speed of molecules in a sample of gas to double. By what factor do you need to increase the temperature of that gas? Okay, so to answer this question, I would go ahead and set up two cases. So let's do our first case, V RMS1 is going to be equal to the square root of 3K, the original temperature, I'll call it T1, divided by M. And then we're going to have VRMS2, which is our second case. Here we're going to set that equal to 3K T2 divided by M, where the only thing that's changing between case 1 and case 2 is the temperature. That's what we want to change here to change our root mean square speed. Okay, and then we know that we want this VRMS2 to be equal to 2 times VRMS1. And then we know that VRMS1 is equal to the square root of 3KT1 times M. So in other words, here we're going to set this equal to 2 times the square root of 3KT1 divided by M. Okay, now what I want to do is I want to compare the temperatures, and so to do that, I'm going to go ahead and square both sides. So when I square both sides of this equation, when I square the left-hand side, I'm going to end up with 3KT2 divided by M. And then when I square the right-hand side of this equation, don't forget to square that 2 out front there. So we end up with 2 squared multiplied by 3K T1 divided by M. Okay, now our 3's, our K's, and our M's all cancel. And what we end up with here is T2 is equal to 2 squared, which is 4, multiplied by T1. Okay, and so that means that we want to increase the temperature of the gas by a factor of 4. So I would go ahead and pick answer C here. Okay, so our next topic for today in our discussion of thermal physics is what happens at a phase transition. Okay, so just a quick review on the phases of matter. We have 3 phases that we're all pretty familiar with, I think. So we have solid, and then we have liquid, and finally gas. The 4th phase of matter is actually called a plasma, so this is something that's maybe a little bit less familiar, but there are familiar examples of a plasma. A plasma is really just an ionized gas plus then the free electrons. So ionized just means the electrons have been removed, so they're free in the gas. Okay, so everyday example of a plasma is actually the gas inside a neon sign. It's really a plasma. The electrons have been removed from the neon atoms, and so it forms a neon plasma. Another example of a plasma is called the stellar corona. So around our sun, it's called the solar corona. So the sun is like that circular shape, and then you can see how there's like this hazy fringe around it. And so that is actually what we can see is actually the plasma that surrounds the sun. So this is due to the fact that the sun is really hot, and so the gases surrounding the sun are ionized and they form this plasma around the sun. So we can visualize it as this stellar corona here. Okay. All right, and so now that we've talked about the phases of matter, we can think about transitions between the phases. Again, we have some very familiar phase transitions. So going from solid to a liquid is melting. Going from a liquid to a solid is freezing. Going from a liquid to a gas is boiling or evaporation, and then gas to liquid is condensation. So those are probably very familiar. Something maybe less familiar is sublimation, which is when you go straight from a solid to a gas. That is an example that you're maybe familiar with is dry ice. So dry ice does sublimate at room temperature. And so this is just the solid form of carbon dioxide, and it sublimates directly into carbon dioxide gas. Okay, and then the transition from a gas to a plasma is ionization, and backwards is deionization. Okay. All right, so now we want to ask ourselves, what are the necessary conditions to cause a phase transition? And to think about this, I just have a quick kind of fun video. So we'll go there for a moment.
Okay, I'm going to do an experiment, sort of like physics with beer. As you can see, there's a bottle of Corona here, which has been in a freezer, but it's still liquid. When I open the top of it, and change the environment a bit, start to see it's just freezing up all the little beer molecules. Just need to next to each other. Just freeze and change from the liquid state to a frozen state.
Okay, so what did we see in this video? So first of all, we had this very cold beer in a closed bottle and it was in its liquid state. And then as soon as he opened the bottle, it started to freeze, right? And so what is the difference between the closed bottle and the open bottle that allowed the beer to freeze? It's clearly not that it was colder, right? So he's not doing anything to cool it down. So what's the difference between those two that causes the beer to freeze? So the answer is really the pressure. So when the bottle is open, the pressure decreases and the beer starts to freeze, whereas it's in the liquid state when the bottle is closed and it's at a higher pressure inside. And so why is this the case? Well, it's because phase transitions depend on both temperature and pressure. So you have to be at a particular temperature and a particular pressure to cause a phase transition. All right, and so then the way that we can visualize when phase transitions will occur in terms of pressure and temperature is with a phase diagram. So I have an example here of a typical phase diagram. So you can see that there are several different lines on this phase diagram, which we will go over in detail in a later slide. But the general idea is you can see that the different phases are marked and they're separated by these lines on the phase diagram. And this phase diagram just has temperature on the x-axis and then pressure on the y-axis. Okay, so let's dig a little bit deeper into these phase diagrams. So first of all, we have to talk about phase equilibrium. So phase equilibrium is really just when two or more phases can coexist. And when a substance is in phase equilibrium, the total number of molecules that are in each phase has to remain constant. And this type of phase equilibrium is only achieved at a particular pressure at a particular temperature for a given substance. And so then if we were to plot on our phase diagram the lines that separate two phases, those lines then are representative of the phase equilibrium values. So those are what we call the phase equilibrium curves. And we can think about three curves. So back to our diagram over here. The dark red curve is what we call the sublimation curve. So you can see that anywhere below the dark red curve is in the gaseous state, right? So it's a vapor. And anywhere above this red line, you can see we're in the solid phase. And so that line is separating vapors and solids, gases and solids. And so right along that red line, that's where you can have this coexistence of a gas and a solid. So that's where sublimation occurs. All right, then you can see the green curve here is what we call the fusion curve or curve of fusion. And this separates the liquid state is below it, right? So you can see this is our liquid state is anywhere below the green curve. Above it is the solid phase, right? And so this is separating liquids from solids. And so that means that melting and freezing can occur along that line. We can have coexistence of a solid and a liquid state. All right, lastly then, the blue line here, we have liquids up above the blue line and we have gases down below the blue line. And so this is what we call the vapor pressure curve, and boiling and then condensation both occur along that line. All right. So let's take a look at a specific example here. So this is the vapor pressure curve for water. So in other words, boiling and condensation can happen along this blue curve here. So there are several things that are marked on this curve. You can see here that at atmospheric pressure, which is about 100 kilopascals, and a temperature of 100 degrees Celsius, we are right on this blue curve, which is what we would expect because 100 degrees Celsius is what we refer to as the boiling point of water, and we exist at atmospheric pressure. And so that's why we think of the boiling point of water as being 100 degrees Celsius, but really it can be anywhere along this curve depending on the pressure of a given situation. So you can see in a pressure cooker, which increases the pressure, it doubles the pressure compared to atmospheric pressure, the boiling temperature of water is much higher. And this is actually what allows then your food to cook more quickly in a pressure cooker because the water is actually hotter in the pressure cooker than it would be if you were like boiling on the stove. Okay, and so I've already talked about this a little bit, sorry. So above the curve means that we are going to be in a higher pressure state than below the curve. And so higher pressure to me makes me think of molecules getting squished more together. And so that tells me that above the curve should be the liquid state, right? So that should be liquid water, because the water molecules are more pushed together in a liquid state than in a gaseous state. And below the curve, we're going to end up having a less dense material, right? Because you're lower on the y-axis, so that will be a less dense material. And so that would mean that gas is favored below the curve. And of course, along the curve, that's where we said we have either condensation or we have boiling occurring. All right, so let's take another close look at a phase diagram here. So you can see we've pointed out already quite a few of these things. So we've already talked about the sublimation curve, which separates solids and gases. Then you can see here we have the fusion curve, which separates solids from liquids. We have the vapor pressure curve separating liquids from gases. And then there are a few more details that I wanted to point out on here. So the first is this triple point. So you'll notice that this is this red point here, where our three different phase equilibrium curves, so the sublimation curve, the fusion curve, and the vapor pressure curve, all meet at this one point. And so you can actually see that liquids, solids, and gases all surround this point. So what that means is that you can have liquids, gases, and solids all coexisting when you're at this one unique temperature and pressure. And so then that temperature and pressure specifies the location of this triple point. Okay. Next up, I wanted to point out this critical point. So you'll notice gas is blue, liquid is yellow in this diagram, and then we get just fluid, and it turns green. So what does this mean? So at the critical point, at this particular temperature and pressure, anywhere beyond that critical point, so for any temperature higher and pressure higher than the critical point, it turns out that the densities of liquids and gases of that particular substance are the same. And so we don't really think about it as being a liquid or a gas, but instead a supercritical fluid. And so if you're interested in supercritical fluids, I do have a YouTube video here you can watch, and you can see the transition from the coexistence of a liquid and a gaseous phase into this supercritical state. It's kind of interesting. So if you're curious, I highly recommend watching the video. It's a little bit long, but you can kind of like scan through and look for the interesting parts. Okay, and so then I just wanted to point out one kind of interesting and strange thing, which relates back to our original video. So here we have a curve. This is going to be a fusion curve, and you can see that the solid state is below the liquid state. So the solid state is actually at a lower pressure than the liquid state. So can you guess what material this curve corresponds to? Something looks different here. Something looks funny. Okay, so if you guessed water, you are right. We keep talking about how strange water is, and this is it again. So the reason why this curve looks a little funny is because in general, you'll have something that looks like this. So you have a positive sloping fusion curve. So in other words, the solid state is above the liquid state. In other words, the solid state is favored at a higher pressure compared to the liquid state. All right, so why does the fusion curve have this negative slope? Why is the solid state below the liquid state for water? This goes back to the fact that the density of water actually decreases when you freeze it. So this is something very unique. It doesn't happen for many substances. Most substances become smaller when you freeze them. Not water, it expands. And so that's why we have this strange state. It's also why when you popped the top on the beer, it froze because it was at a lower pressure, right? So lower pressure means that you get this expansion and we get this freezing. Okay, so water, very strange, very interesting, but thank goodness, right? All right. Okay, so next I just wanted to talk quickly about evaporation in terms of sweating. So the question we wanted to answer here is, why does sweating cool you down? So we're just going to think about the physics of this kind of quickly. So here I have a glass of water, which is kind of representative of like a water droplet on your skin. So that's what we want to think about here. And so the basic idea of why sweating cools you down is because you have this drop of water that sits on your skin, and it contains molecules, right, that are bouncing around in there. And what ends up happening is that the molecules with the highest speeds are able to escape from the water droplet. And so they go into the gaseous phase. All right, and then that means that we end up with this equilibrium between the gas and the liquid, so like the water vapor that sits right over that sweat droplet and the water that's actually in the sweat droplet. You get equilibrium between those two states. But then you can imagine some sort of cool breeze or something comes and it sweeps away those water molecules that evaporated up from your water droplet. And so then you have fewer than what you need for equilibrium, fewer water molecules in the gaseous phase than you have in the liquid phase. And so what ends up happening is that more water molecules, more of those high energy, high velocity water molecules will end up evaporating so that you regain that equilibrium state between the number of molecules that are in the gaseous phase and the liquid phase. And this keeps happening, and what ends up ultimately happening is that all of the really fast molecules, or more of the really fast molecules, have escaped from the water droplet. And we already talked a little bit about the relationship between the speed of the molecules in a substance and temperature. So remember, for an ideal gas, those two things are directly related to each other through the kinetic theory of a gas. They're always related. The relationship just becomes a little bit more complicated when it's not an ideal gas. But the basic idea is that those faster moving molecules correspond to a higher temperature. And so when they escape, they leave the water droplet at a lower temperature. Okay, and so then that cooler water droplet is in thermal contact with your skin. And so then it's at a colder temperature than your skin. And what ends up happening then is we know that we will have heat flow from the hotter skin into the colder water droplet, and that pulls the heat away from your body and it cools you down. So a little bit of interesting physics on why sweating cools you down. All right. So now we want to talk a little bit more about the physics of a phase transition. Specifically, we're interested in knowing how much heat is required to cause the phase transition of a particular mass of a particular substance. And this is characterized by something called the latent heat. It's given the symbol L, and L is just equal to the heat required for the transition. So here I'm calling that Q trans, divided by M, which is the mass of the substance. Okay, so it will have units of joules divided by kilograms because Q, remember, is energy, so it has units of joules. Mass has units of kilograms. So this is the type of thing that you will look up in a table, and there are 3 different types of latent heat for every substance. So if we're talking about a transition from between a liquid and a gas phase, then we call it the latent heat of vaporization. And this corresponds to if you have boiling or condensation, you'll want to look in a table for the latent heat of vaporization. If instead you're thinking about a transition between solid and liquid states, in other words, if you're thinking about melting or freezing, then what you need to look up in a table is the latent heat of fusion. And finally, if you're talking about sublimation, so change between a solid and a gaseous phase, then you need to look up the latent heat of sublimation. All right, so like I mentioned, it's something that you will either be calculating or looking up in a table. It's one of those sorts of characteristic properties of a substance. And so you can see I have a table here. We have, for example, the latent heat of fusion and the latent heat of vaporization for water. So you can see that actually the latent heat of vaporization for water is an order of magnitude bigger than the latent heat of fusion. So in other words, to boil off the same amount of water requires more energy than it does to melt that same mass of water from ice into water. Okay, all right. And so let's think a little bit more carefully about latent heat and what this means in terms of the heat added to a substance and the change in temperature of a substance. So during a phase transition, what you're doing is you're adding heat to the substance, but that heat, that energy that's added is heat. It's really just going into the energy that's required to cause the phase transition. And so phase transitions always occur at a constant temperature. If you think about it, we talk about boiling water at atmospheric pressure. We talk about it being at 100 degrees. But the whole time you're boiling water on the stove, you're adding heat to the water, right? So you've got that flame underneath your pot. You are continually adding heat to the water, but the temperature is just staying at 100 degrees. And so why is that? It's characteristic of phase transitions. You don't have a change in temperature, even though you're adding all this heat. And that's just because all of that energy is going into the phase transition itself. Okay, and so if we think about, put a pot of water that's from the tap on the stove and you turn on the flame, what happens to it? Well, first of all, you're going to heat up that water. So you're going to initially get a change in temperature that corresponds to Q, the heat that you add, divided by MC, where C is the specific heat of water. So originally, when you're not at that boiling temperature, when you add heat, you just get a change in temperature of the water. Then as soon as you hit that boiling point, as soon as you hit 100 degrees Celsius, what ends up happening is that all of the additional heat that you add to your water just goes into boiling it. So it goes into transitioning the water from liquid water into steam. All right, and then once you have boiled off all of your water, then if you keep adding more heat, what ends up happening is you just end up heating up the steam, right? So once you run out of water, you've boiled it all off, and all you're left with is steam, but you keep adding heat. Then once again, you get a change in temperature due to that added heat that's going to be equal to Q divided by MC, where now C is going to be the specific heat of steam. So the different phases do have different specific heats, so you'd have to be careful about that. All right, and so then this amount of heat that's required between having all water and having all gas, that's what we call latent heat. So in this case, that would be L multiplied by the mass of water that you're boiling off. All right, let's do a quick practice problem. So what will do a better job of cooling your beverages? A cooler that's filled with water or a cooler that's filled with ice, and both the water and the ice are at 0 degrees Celsius. And I have this image here to make you think about latent heat in terms of this answer. So the key to this is knowing that the warmer beverages are going to give off heat to whatever you have in your cooler. So whether it's the water at 0 degrees Celsius or the ice at 0 degrees Celsius. But if you have ice at 0 degrees Celsius, that heat is first going to go into melting the ice, and then it's going to go into warming up the water that remains after the ice has been melted. Whereas if you start with just water at 0 degrees C, then all of the heat that's being taken from those warmer beverages is all going to go into heating up the water. And so you'll reach the same temperature more quickly than if you had started with ice. And so ice is going to do the better job of cooling down your cold beverages or your warm beverages. It's going to do a better job than water, even though they're both starting at the same starting temperature of 0 degrees Celsius. And it's kind of weird to think about water being at 0 degrees Celsius. When we think of 0 degrees Celsius, we think of ice, right? But actually they can coexist at that temperature. So if you think about like an ice bath, right? So you've got water and ice mixed, and they're both at 0 degrees Celsius. So they can both coexist at 0 degrees C. And ice itself can be much colder than 0 degrees C. I think that's another thing that's kind of hard to think about. Ice isn't just 0 degrees Celsius. It can be much, much colder than that. 0 degrees is just where we have this transition happening. You can have coexistence of water and ice at atmospheric pressure. Okay, let's do one more latent heat example. This one's more of a calculation. So we want to know how much energy is required to boil off 1 cup, and I've given you the volume of 1 cup of water here. It's 2.4 times 10 to the negative 4 meters cubed, and you're going to need to use the values provided in the table here. The key to this problem is that we're talking about boiling. So first of all, boiling is a phase transition, which means that we are not interested in the specific heat here. Specific heat is when we are adding heat to an object and we're causing a temperature change. Here, our added heat is going into the phase transition, and so we're not interested in specific heat. We don't have a change in temperature here. What we're interested in then is latent heat, And specifically, since we're talking about the phase transition between liquid and gas, what we're really interested in is the latent heat of vaporization. So then we know that Q is going to be equal to latent heat of vaporization, I call that LVAP, multiplied by the mass of the water. Here we have the volume of the water, right? And we also know the density of the water. And so since we know density and we know volume, we can calculate mass. Remember, density is mass divided by volume, and so that means that mass is going to be density times volume. Okay, so all we have to do now is plug in our numbers. So our latent heat of vaporization is 2.3 times 10 to the 6 joules divided by kilograms. Density of water is 1,000 kilograms per meter cubed. And then our volume of water here is 2.4 times 10 to the negative 4 meters cubed. Okay, and so when you end up calculating that out, I ended up getting 550,000 joules. And so I picked answer A here. All right. So that's it for our chapter 17, which was all about the ideal gas and phase transitions. And now we're on to our very last chapter of the semester. So we're going to finish it up with talking about the laws of thermodynamics. All right, so we've actually already talked about the zeroth law. We've already mentioned the laws of thermodynamics. So remember, the zeroth law is just that when two objects are in thermal equilibrium, they have the same temperature. That was our zeroth law, where this is telling us basically how thermometers work, right? So you can always think of like a thermometer when you think of the zeroth law. All right, and so then we're going to spend the last few classes here talking about the first and second laws of thermodynamics, and we'll just briefly mention the third. Just for completeness, we're going to mention the third. Okay, so before we get started on the first law of thermodynamics, we need to get some really clear definitions of heat, work, and internal energy. Okay, so let's start with heat. Heat, Q, remember, is energy transfer between objects at different temperatures. So really, when we think about heat, we think about the spontaneous flow of energy from a hotter object to a colder object. Okay, next up we can talk about work. So when we think about work, earlier in the semester we defined work to be energy transfer due to an object being acted on by an external force over some displacement. Okay, and so remember we had the equation work is equal to F d cosine of theta, where F is the force, d is the displacement of the object during the time that the force is acting, and theta is the angle between the force and the displacement. Okay, so we're still going to be using that definition, but now in terms of thermodynamics, we really say that work is any transfer of energy that isn't heat. Okay, our last thing that we need to define here before we can move on to our first law of thermodynamics is internal energy U. So internal energy U is the total kinetic and potential energy in a system. So it contains several different energy terms. All right, so the first energy term that's included in the internal energy is the kinetic energy of individual molecules in the system. So this is really like random, disorganized motion at the molecular level, and we're thinking about the kinetic energy of each individual molecule in the system and adding it up. And that's going to be one component of the internal energy. So gases, liquids, and solids will all have a component of the internal energy due to this random motion of the individual molecules in the substance. Okay, then when we're thinking specifically about a monatomic ideal gas, so remember a monatomic ideal gas is one that has just a single atom per molecule, then it turns out that this is the only type of non-constant internal energy that monatomic ideal gas has. So when I say non-constant, that comes in because really when we're thinking about internal energy, what we're going to be interested in is a change in internal energy. So there are some other constant terms, but when we think about a change in internal energy, those terms are going to cancel out. And so this is the important term that we're going to be focused on. All right, so what is then the internal energy for a monatomic ideal gas? Well, really, it's just going to be the sum of the kinetic energies of every molecule in that ideal gas. So then when I think about the sum of the kinetic energy of every molecule, I can approximate that by just multiplying the average kinetic energy per molecule by the number of molecules in the gas. Okay, and then we remember from our kinetic theory of a gas that we actually know the kinetic energy, the average kinetic energy per molecule. So remember that average kinetic energy per molecule is 3/2 kT. All right, and so then what I just need to do to get the total internal energy for this monatomic ideal gas is multiply that average kinetic energy by the number of molecules, which remember is capital N, and so we end up with 3/2 NKT. Okay, and then we can additionally remember the ideal gas law, which tells us that PV is equal to NKT. And so what that means is we can replace the NKT with PV. So in other words, another way that we can write the monatomic ideal gas internal energy is 3/2 PV. And this is going to be very useful for us because oftentimes we're going to be interested in looking at pressure versus volume diagrams. And so then we'll be able to read the internal energy for a monatomic ideal gas right off of this diagram. Okay, so now let's think about some other terms that will contribute to the internal energy when we have systems that are composed of things other than monatomic ideal gases. So it turns out that there are some other forms of kinetic energy that will also contribute, so specifically vibrational and rotational kinetic energies. Okay, and then by including vibrational and rotational kinetic energy, it turns out that we can derive the internal energy for a diatomic ideal gas, where remember a diatomic ideal gas is one in which the molecules are made up of two identical atoms. So these are things like oxygen gas, O2, nitrogen gas, N2. Those would both be examples of diatomic ideal gases. Okay, so then it turns out that the internal energy for a diatomic ideal gas in the low temperature limit, which just means not very, very high temperatures. So these are going to be at normal temperatures. Then it turns out that U is going to be equal to 5/2 NKT. Once again, we can use the fact that for an ideal gas here, we have NKT equal to PV, and so we can write this as 5/2 PV. Okay, and then if we want to think about real gases and liquids and solids, we also have to include in the internal energy some terms due to potential energy, which comes from the intermolecular forces of attraction between atoms in those substances. All right. So now we're ready to talk about the first law of thermodynamics, which really is another statement of conservation of energy. So we've done conservation of energy quite a few times in this class. This is really another specific example of conservation of energy. So specifically, this first law of thermodynamics tells us that the change in internal energy of a system, so that's delta U, is equal to the heat flow into the system, which we call Q, minus the work done by the system, which we call W. Okay, and so then we end up with delta U is equal to Q minus W. All right, and I'll just mention here I have underlined that W in this case is the work done by the system, and so we'll just want to keep that straight because we can think about work done by the system and work done on the system. So we'll talk a little bit more about that in a moment. Right now, I just want to mention some important sign conventions that are associated with this first law of thermodynamics. So first of all, let's talk about sign conventions for Q. So Q is going to be positive if the heat is flowing into the system. And the way I remember this is by thinking about the fact that if Q is positive, it's going to contribute to an increase in the internal energy of the system. So that corresponds to energy going into the system. Okay, so that's how I remember that sign convention. Alternatively, if Q is negative, that corresponds to heat flowing out of the system, which is going to decrease the internal energy of the system. All right, I think the Q one isn't quite so bad. The work one, like I've already alluded to, is a little bit trickier. So when we think about work here, specifically work done by the system, then this work done by the system is going to be positive if the force exerted by the system is parallel to the displacement. Okay, and so we're going to want to think back to that equation W is equal to FD cosine theta, where theta is the angle between F and D. And so here we're going to end up getting positive work in the case that the force and the displacement that it causes are parallel to each other. In other words, they're in the same direction, and that's when we get that theta in our FD cosine theta of 0. Okay, so whenever that's the case, we get positive work done by the system. We're going to get negative work done by the system if the force exerted by the system is in the opposite direction compared to the displacement that it causes. All right, and so then similar to when we were thinking about Q, we can think about this work in terms of what happens to the internal energy of the system. So when the work done by the system is positive, that means that the system is putting out energy. Okay, and so that means it's actually decreasing the internal energy of the system when the work done by the system is positive. Alternatively, when the work done by the system is negative, that actually is going to correspond to energy entering the system. So in other words, that's the case where you're going to get an increase in the internal energy, delta U. Okay, and then the tricky thing to remember when we're working with this first law of thermodynamics is that in the equation in the blue box, W is defined to be the work done by the system. But work done by the system is going to be related to, in fact, it's going to be equal and opposite compared to the work done on the system. All right, and so that really comes from Newton's third law. Remember, if you have a force exerted on an object by another object, then the other object exerts an equal and opposite force back on the original object. So it's one of those situations here. So we have the work done by the system is going to be due to the force exerted by the system. However, there's going to be an equal and opposite force exerted on the system that's going to do an equal and opposite amount of work on the system. So we just have to be really careful when we're thinking about the sign of the work to remember that we're always thinking about the force exerted by the system and its direction and not the force exerted on the system. All right, we're going to do some practice with that, so don't worry. Okay, just a few last things to talk about in terms of this first law of thermodynamics, just some specific properties of delta U, Q, and W. Okay, so first of all, when we're thinking about delta U, I'll just remind you that we already know U for a monatomic ideal gas, it's 3/2 NKT or 3/2 PV, and for a diatomic ideal gas, we know it's 5/2 NKT or 5/2 PV. Okay, and so then when we think about delta U, what we can do is we can define some initial and final internal energies using these equations up above, and then we just subtract them to get the change in internal energy for an ideal gas. Okay, so those are some really nice relationships. Okay, and then one last important property of delta U to point out is that delta U is only then going to depend on those initial and final states that you define for your system. So it doesn't depend on any values of the internal energy in between. It doesn't matter how your system gets from one state to another. All that matters is the initial and final state when you calculate delta U. And the reason why I mention this is because that's not the case when we talk about work and heat. So it turns out that the amount of work done by the system and also the heat flow into the system will both depend on how the system reaches a given state. So in other words, it's going to depend on the process by which your system is transformed from some initial state into some final state. All right. Let's wrap up for today by just doing a little bit of practice. So here we want to think about these sign conventions. So specifically, we want to know the work done by a gas as it expands is positive, 0, or negative. Okay, so to answer this question, I would think about the equation work is equal to force times displacement times the cosine of the angle in between the force and the displacement, right? So theta is that angle between F and D. Here specifically, we're thinking about the work done by the gas as it expands, which means that when we think about the force, it needs to be the force exerted by the gas. Okay, so let's think about the direction of the force exerted by the gas, the direction of the displacement, so we can think about this angle theta. All right, so first of all, when I think about my piston here that's sitting in this cylinder that contains a gas, it turns out then that the force exerted by the gas in both cases is going to have to be pushing upwards. And we know that because otherwise that piston would just fall to the bottom of the cylinder, right? So if that gas wasn't there exerting an upward force on it, we know that that piston would just fall due to the effect of gravity. Okay, so there must be a force upward on that piston in both cases, both the initial state and the final state. Okay, then we can also think about the resulting displacement due to that force exerted by the gas. So here that's going to be the displacement of the piston. So it starts at some initial position and then it raises up to some final position for the final state due to this expansion. And so I would say that the displacement here is a vector that also points up. All right, so then when I think about force and displacement and the angle between them, they're both going to be in the same direction. They're both pointing up. And so that means that theta is going to be equal to 0. So then we end up with cosine of 0. In that case, we're going to end up getting positive work. Okay, so I would say that the work done by the gas as it expands is going to be positive. All right, that's it for today. We're going to do a lot more practice with this in class and also next time. So I will see you guys then.